So in this lecture, we won't talk about more on recursion. So first of all, we'll start with strings. So we have seen examples of using lists. We have seen examples where we were just using numbers. We have seen multiple examples in both of them. Now I want to solve a couple of problems which involve strings, and then we will get back to lists where we'll be doing merge sort, quick sort, and problems like those. Right? Perfect. So let's start with the problem related to strings. So the idea is, or I should say, the problem is that we are given a string, right? And you're given two characters. Let's say character A and character B. Right? So in Python, everything is a string, but I'm assuming these are single characters. Okay, perfect. So you have this string. You have to replace all the occurrences of A with B. So wherever you have A, you need to replace that with B. Okay, perfect. So we can do it iteratively, but I want to do it recursively again for the same reason, because now if you use it like solve this problem using recursion, you will get more comfortable with strings and recursion, and then later on when we are solving harder problems, it will be easier for you. Okay, so how should we do this? Now I have a string. I want to replace character A with character B. Okay, let's talk about the base case. Length 0. Do nothing, right? We can just simply return this original string that we get in case of length 0, which is the empty string. Okay, hypothesis. Our function can do this for L-1 sized strings, right? That's my hypothesis. Induction step. So now, given a string, I can assume I can call recursion on this part of string and things will work fine, right? Things will work fine. Okay. So my only work is this first character. I need to take care of this. So first of all, we need to remember that strings are immutable. So you cannot change this original string. You need to create new strings whenever you want to do any kind of change. Okay. So because strings are immutable, we will not be using the start index approach. We can use the start index approach, but it's not really required here because you will be creating so many new strings anyways. Okay. Because for the output also you need to create a new string. Perfect. So now, what I'll do is, I'll call on this part first, I'll get a smaller output, which I'm assuming will have all the occurrences of A changed by B. Then I will check, if this character is A, then I need to return this. If this character is not A, my original input's 0 character stays the same, and I need to attach smaller output string along with it. Right? So whatever changes smaller output has been done with respect to this, that stays either ways. Anyways, that's going to stay. Those changes are going to stay. Whether to change the first character or not, that depends upon if s of 0 equal A. In that case, I need to return this. Otherwise, I need to return this. So for example, if I have, let's say A is C and B is X, and you have D written here, then you just keep D as it is, and you attach D with smaller output, right? And you return that. That's what we need to do. Okay, let's quickly write this code. Perfect. So I'm writing replace char. I'm going to get a string. I'm going to get A and B. So this is what needs to be replaced with B. Okay. First of all, my base case, if length of S equal 0, return S. And we need to return the changed string. So we are returning the changed string. So if length is 0, we return the empty string itself. Perfect. What next? Now, irrespective of what is in the first character, we need to call for the smallest string. So small output is replace char. Second and third argument will stay the same. The first argument should be the smaller string, not the complete string, the smaller string. So I can do slicing to achieve that. So this is my smaller string that is going for small output. Okay. Now when you have the small output, what do you need to do next? You need to check if the first character needs to be changed. So if s of 0 equal A, if these strings are same, in that case, I need to return, instead of A, it needs to become B, right? So I need to return B plus small output. In case it is not A, I can't return S, right? So for example, C needs to be replaced with X. This is D, A, C, B, X, C, D, right? So now when I call small output, when I call replace character on small output, these are already replaced with X. So just because this is not C does not mean I can say else return S, because in that case I would return the original string, which will be incorrect. So I need to keep this character, but the changed output that I received from this call, I need to keep that changed output. Okay, so this, and I need to attach the 0th character here, and that's what we are going to do. So what do you need to do? You need to return s of 0 plus small output. Perfect. Let's check it. Let's take the same example that we have taken here. DAC DX CD, and I want to replace C with X. And that's what we wanted to get. That's the answer we wanted to get. Okay, just to check the edge cases, let's try on this. Perfect. There was no C, so no replacement. This works fine as well. This works fine as well. Everything seems to be working fine. And this is perfect. So seems like this is what the correct function is, and just make sure that you understand what exactly is going on, right? So strings are a little interesting because they are immutable, so you need to make sure that you're picking up parts from here and there and you're attaching them correctly. Okay, thank you. Hi, so let's pick up another problem on strings. Hopefully that will make things a little more clear, right? So not very hard problem. Basically what we want to do is we are given a string, and whenever you have pi, right, small p n followed by small I want to replace that with 3.14. So if you give me ABC pi, DEF pi, then what's going to happen? I'm going to replace that with 3.14 DEF, 3.14, 3.14, P, 3.14. That's what the output should be. That's what we need to do. Okay, so that's what we need to do. It's basically very similar to the replace character one that we have seen. Now what you need to do is, I think the base case will be a little different. If the length is 0 or the length is 1, you return the same string. Nothing needs to change, because a single length string cannot have pi in it. Okay, so your string now has minimum 2 length. Okay, so what we need to do is, we'll check if the first character and the second character is pi. Then we need to remove this and make it 3.14, and the rest of it can go into recursion. In case the first 2 characters are not pi, I think we should just remove the first character and call recursion on rest of it. For example, it's possible that you have a string like this. Now the first 2 characters are not pi, but if you remove 2 characters, that'll be a problem. So you need to remove only 1 character and call ahead. But in case the first 2 characters are pi, then you can just remove these 2 and replace them with 3.14. Okay, so that's what we need to code. Let's do it. Replace pi, you want to get only 1 string. Okay, so if length of s equal 0 or length of s equal 1, we need to return s. So this is basically your base case. Now base case is done. So now I need to look at the 0th and the first character. So if s of 0, and I'm not worried about looking at the first 2 characters because I know the length will be minimum 2. It's not 0, it's not 1. So the length has to be minimum 2. So you can check the 0th and the first index. You will not get an error. So if s of 0 is equal to p and s of 1 is equal to I, that basically means you are starting with a pi. You want to find the small output. Small output will be replace pi, and in this case I want to remove the first 2 characters, not the 1 character, 2 characters. So I am passing starting from 2 till the end, and then I can return 3.14 plus small output, right? Else, if the first 2 are not pi, I need to get the small output, but this time I can't remove 2 characters, I need to remove only 1 character. And then whatever is the small output, I need to attach that first character again into it and return. Right? So let's say you have b pi d. Then here you call on pi d. Whatever return you get, you attach d in front of it. So the small output will be this, right? So you attach d in front of it and then return. Let's try it out. Let's call reverse pi on ABCD. Nothing should change. Let's call it on pi. It's making it 3.14. Let's do this. It's making it 3.14, 3.14. That's perfect. This should also work. This is also working. Seems like this is also fine, right? This is I think perfect code. Works absolutely fine. And I hope you understand how did we decide whether to pass, whether to remove 1 character or 2 characters, and then we worked accordingly. Okay, perfect. Thank you. Hi. So in this session, I want to talk about a very interesting algorithm to search something in an array. It's called binary search. I hope you know what binary search is. I'll give you a quick explanation of what binary search is, and then we'll try to write code for it. Okay. So given an array, or in case of Python, given a list, we want to binary search it. So first of all, binary search has a condition. List must be sorted. So in case you want to find something in your list, what you will have to do is, if you use linear search, you will have to pass through the complete list one by one. Binary search makes things faster, but it requires the list to be sorted. What is the concept behind it? So binary search basically says, in case of linear search, if I have 1000 elements, I need to look at 1000 elements to figure out if my element exists there or not. In the worst case, if my element is not present, then I need to go through everything to figure out if it is actually not there. Binary search says that you can take advantage of the fact that the array is sorted. Okay, so it says let's go to the middle. Let's say I'm looking for 10. Let's go to the middle, and if the middle character, or sorry, middle number is 15, then I know I don't have to look for 10 on this side. Because the array is sorted, there is no point looking for array on the right side because everything on the right will be bigger than 15. So you can only focus on this left part. Similarly, if I go to the middle and I find a 5, that means there is no point looking on the left side and you can just focus on the right side. Now, let's go back to the original assumption that it is 15. Now in this half-sized array, you can again go to the middle element and check what value is there. So this one is 15. Let's say you have 12 here. That again means there is no point looking in this part. You can go and focus on this part. Now let's say I go to the middle and I find a 5. That basically means 10 has to be somewhere in the middle and this part is gone again. So every time you check with an element, you are able to get rid of half the elements. And this half of elements is super fast. So for example, 1000 will reach 1 within 10 comparisons because after every comparison you're doing it half. So 500, 250, 125 and so on, within 10 steps you will reach 1. So you don't have to compare with 1000 elements, you just need to compare with 10 elements. It's amazing fast, right? It's super fast. So this is how we can use binary search. We could do it iteratively, but in this session we'll be doing it recursively. Okay, so how do we do it? So I have a list. I compare to the middle element. I need to find something, I need to search something. Let's say I need to search for x. So I go to the middle element, I compare it with x, and now I know whether I need to go to the left side or the right side. Right? I know whether to go to the left side or the right side. So in the previous lecture we saw two options for this. If you want to go to the right side, let's say this is the area you want to go, this is negated, then one option is that I can make a copy of it. But if you make a copy of it, that actually we end up losing all the benefit that we have with binary search, because copying takes time, right? So I don't want to copy it. So I'm going to call the same function and I'm going to give it the start index. Okay, so what can happen the next time? You again go to the middle and let's say you figure out this area is useless and this is where you want to search. Now in your list, you don't only require start index, you also require the end index, because you want to tell, hey, you can search only from this area to this area, don't go here and there, only stay within this area, right? So binary search is an example where we'll have to pass the list, we'll have to pass the start index, we will also have to pass the end index, and this start and end will tell us what is the search area right now. So initially the search area is 0 to L-1, and slowly the search area will reduce. If the search area becomes empty, if there is nothing in the search area, that basically means that you could not find the element, and as long as there is something in the search area, you keep looking for your required element. Okay, so let's write code for this. Okay, binary search, we're going to get a list and we're going to get x that we want to look for. Let me name it A because I like L to be used for length, and we need to pass the start index and the end index. Okay, so initially the start index will be 0 and the end index will be length of A minus 1, because that's the search area, 0th index and the last index. This is the search area. Okay, what is my base case? I think my base case is when the list is empty. When is list empty? Can I say my list is empty? Can I say my list is empty if this is the case? I don't think so, because in this case there is one element left. You have start index and this is the end index. That means this is the only element that you need to search for. Any other example where basically what should be the base case then? I think our base case will be this. When start has crossed end, this is start, this is end, that means nothing left. If they are same, there is one thing left. If start is here, end is here, there is these many elements left. But if they have crossed, if start is here and end is here, that means we are done, right? So our base case will be if SI greater than EI, we can return, we didn't find it. We were supposed to return the index where we find it. I'm going to return -1. That we didn't find it, right? If you find it, you will return the index. If you don't find it, you will return -1. Okay, perfect. Okay, now what do we need to do? We need to find the midpoint. Mid is equals to SI plus EI by 2, right? SI plus EI by 2. If you do this, I hope you remember, if you do this, you get 3.5. That's not what you want. You want the index, the exact index, an integer. So we need to do integer division. But let's see. Let's say I have 6 elements from 0 to 5. What will be my middle number, right? 0, 1, 2, 3, 4, right? So you have two middle here. If you do 0 plus 5 integer division 2, you'll get this. So this will be your middle, which is fine. Both sides cannot be equal in this case. In the other case, let's say I have 5 elements. So 0 plus 4 integer division 2 will give you 2, which is perfect, which is your middle number, right? That's great. So I think we'll get the middle if we do this, right? We'll get the middle if we do this. Let me get rid of this. Now what you need to do is, if A of mid equal to x, you return mid. You have found x. That's what you were looking for. So you just return the index where you find x. Okay. The other option is A of mid is greater than x. What does this mean? Mid is bigger than x. That means you can only find on the left side. So you have some boundaries given to you. This is start index, this is end index. You looked at the middle, and a of mid is greater than x. That means x can only be between these limits, from si to mid minus 1 actually. Mid is not equal to x, so you don't have to consider mid in the remaining work. Okay, so else if a mid greater than x, we are going to call binary search on a x. Start index stays same, end index becomes mid minus 1, right? And whatever output you get, that's what you need to return, because we are returning the actual index, right? So it'll tell you if it says that it's at 7, it's actually in 7 in the complete array, not in this subpart. It's giving you the actual index. Okay, perfect. So you need to return this. Else, this basically means that you have this start index, you have this end index, mid is smaller than x, so x has to be somewhere here. That basically means we can call, so starting index becomes mid plus 1 and end index stays exactly the same. End index stays exactly the same. Okay, so I think this should work. Let's quickly call it on one array, right? The array has to be sorted. Don't complain that my function doesn't work if you take the input to be non-sorted, right? And I want to search for, let's say 3, and my start index will be 0, my end index will be, I have 1 2 3 4 5 6 7 8 9 10 elements, so my end index will be 9. Okay, and it says index 1, which is absolutely correct, right? Let's ask it to find 2 for us, and it's returning minus 1, which is correct as well. Okay, so let's quickly try to dry run this and see how exactly is it working. So let's first take the example where we were able to find 3, right? So I'm assuming this is 1 3 5 7 9 11 13 15 16 17, and I'm looking for 3. So initially this was my range, right? Start index is less than end index, so we don't hit the base case, we calculate the mid. So 0 and 9, mid becomes 4, so we come to this number. So we compare with 9, we have 3 is smaller than 9, so it does not hit this, and it goes, sorry, this is the one we did, 9 is greater than 3, right? So we will make a call on this. So that means the same list, the same number, but the end index is now here. So 0 and 3. We again find the mid, which becomes 1, and we end up coming here. In this case, mid is equal to x, so this function returns 1. So we return 1, the next one also returns 1, the next one also returns 1, and that's how we get our output. Okay, so now let me quickly dry run it for, let's say we try and find 19. Start index, end index. You go to the middle is smaller than 19, so your search area is this much. You again go to the middle, you go to 15 is again smaller than 19, so your search area is only 16 17. You go to the middle, which is 16, you again compare, and your search area is still on the right side, so it becomes only 17. So your start index is 17, your end index is 17. So you compare with 17, and it turns out that your middle is still smaller than 19, so you increase your start index to be mid plus 1, which basically takes start index here, end index is here, so start index is crossed end index, and that's how we know we need to stop, and we return minus 1. So that's how binary search is working. If you try and understand all of this, how exactly things are going to go in, and like how exactly the array is going to get smaller, how exactly your SI and EI will work, things will become complicated. So just focus on PMI, just think on the base case, just think of that the smaller problem is going to work fine, and things will be absolutely fine. Just make sure that you take care of induction step and the base case. Okay, thank you. Hi, so in this session, I want to talk about a very interesting algorithm to sort a list. It's called merge sort. Merge sort is extremely fast and much faster than bubble sort, selection sort, insertion sort, and we just want to talk about merge sort because it's a beautiful recursive algorithm as well. Okay, so what is merge sort? Given a list, I want to sort it. So merge sort says that let's do one thing. Let's call sort on this part. Let's call sort on this part. Right? So my original problem is big. I'm calling sort on two smaller problems. And using induction hypothesis, I'm going to assume that they work fine. So first of all, base case. Length 0, length 1. I'm not going to do anything. Length 0, length 1, my list is sorted. So that's my base case. Hypothesis, I can sort a list using merge sort up to length L minus 1. Right? Now for length L, what are we saying? That make the list into two parts and call merge sort on both of them. So using induction hypothesis, we should be able to sort both of them. Now once you have sorted both of them, this is sorted, we merge these two sorted lists into another list which will be sorted. So the problem now is that you have two lists which are sorted and you need to merge them into one bigger list which is sorted as well. I hope you have done this problem somewhere, and this is a very standard problem that you should have seen in case of lists or arrays, right? So let me just quickly give you an idea. So merging two lists is actually a very interesting algorithm which has application in a lot of places. So the way we can do this is, let's go to the first element of both, 1 and 2. 1 is smaller than 2. See, this is sorted, this is sorted. So the smallest element of this list has to be here. The smallest element of this list has to be here. So to find the smallest overall, you can just compare these two. So let's compare these two. The smaller one comes here and move this variable to the next number. Now from the remaining numbers, the smallest of this list is here, the smallest of this list is here. So you again compare these two, put the smaller one here and move it a little. You then again compare, 3 comes here, you move it here, 4, 5 you compare, 4 comes here, 5 and 6 you compare, 5 comes here, and this list is done. Now as soon as the list is done, you can just copy rest of the other list into the output array, and we are done, and this is sorted, right? So you have two lists, you pass through first list, you pass through second list together. You compare the first element of both of them, copy the smaller one and move in that particular list. That's how you can merge two arrays into one, two sorted arrays into one bigger sorted array. Okay, so again let me just brief you how we are going to do merge sort. So you have one array, right? You have one array list, whatever, you have one array and you want to sort it. So what can we do? It says sort the first half, sort the second half. When both of them are sorted, you don't have to worry about how they will get sorted. They will get sorted because of induction hypothesis. You merge these two into a bigger one, a bigger list, and that list will be sorted. The way I would recommend you to code this would be this: take two smaller lists, copy from here to here, copy from here to here. Okay, call merge sort on this, call merge sort on this, and this will become sorted. Now use these two as your input to the merge to sorted algorithm that we just discussed, and merge these two into the original list that you have. Right, whatever original list that you had, just copy the data back into that particular list. Okay, so you make a copy of the first half of this, you make a copy of the second half of this, and then basically you call merge sort on this part, merge sort on this part. Due to induction hypothesis, I can assume this will become sorted, this will become sorted, and then you merge both of these into the original list that we had. Okay, so basically your code will look something like this: merge sort, will find the mid, right? You need to find the mid, then you make a smaller one list, smaller 2 list, you call merge sort on smaller 1, you call merge sort on smaller 2. Now S1 and S2, both of them are sorted. Then you call this merge on S1, S2 and the original L that you had, so that both of these are merged into this original list that you had. Okay, so that way the original list is now sorted. That's what you want, right? You don't have to return anything. I'm giving you a list and you need to sort it, because lists are mutable. You can actually change the data within it, so you can sort this list itself. Okay, a beautiful algorithm which is very recursive in nature and works really, really well. Okay, please code this and it'll give you a lot of confidence. I'm sure you'll really enjoy it. Okay, thank you. Hi, so let's write code for merge sort. Okay, perfect. So merge sort will get input just a list. I'm going to call it A, and we need to sort it. So the idea that we discussed, we'll first find the midpoint so that we can divide it into two parts. Okay, so I have a list, so the midpoint will be this. Let's just make sure that this is correct. So let's say if the array is of size 3, so 3 by 2, just 1 second, will be 1. So midpoint will be this one, which is fine. Let's say the length is 4, then 4 divided by 2 will basically be 2. So the indices are these. So this is what the midpoint you're getting, right? This is the midpoint that you're getting. So that's fine. I'm just going to make sure that I make equal copies. So I'm going to copy from 0 to mid minus 1 on one side and mid to the end on the other side. Okay, that's what I'm going to copy, because if you're finding mid this way, this is what the mid is coming to be. So I'm going to make sure that I make equal copies. Let's take another example. Let's say I just have two numbers. So length will be 2. This will give me 1. So I need to make sure I make a split here, right? I need to make sure that I make a split here. So up to mid minus 1 will go on one side, and starting from mid will go on the right side. Perfect. A1 is 0 to mid. When I say up to mid, it actually copies till mid minus 1. And A2 is equals to starting from mid till the end, right? So I have A1, I have A2. I'm going to call merge sort on A1, I'm going to call merge sort on A2, and both these will work fine because of induction hypothesis. Do not question this, do not try to go inside as yet, because as soon as you try and go inside into recursion, things will get complicated for you because you haven't written the complete code. Because as soon as you write the complete code, things will be absolutely clear. For now, because this is a smaller problem, PMI tells you that this is induction hypothesis, assume. Okay, please assume. Now, after you have sorted A1 and A2, I'm going to write another function merge, which is going to merge A1 and A2 into A, the original list that we had, and we'll be done. That's it. The two sorted lists that you have, you are merging them into the original array that you had, and that's what we were supposed to do. We were supposed to sort the original array. We don't have to create a new array. We wanted to sort the original array. Okay, so let me create this merge function, A1, A2, and A. So I need to merge A1, A2 into A. So as we discussed, I'm going to take I to be 0, j is equals to 0. I'm hoping you have written this code sometime earlier, so I'm going to be a little quick in this. So I is here, j is here, and as we discussed, we will go through both of these. So I can say while I less than length of A1 and j less than length of A2, while this is true, that I is within limit and j is within limit, as soon as you cross the limit, you can't compare. So you know that you are within the limit, so you can compare. So if A1I less than A2j, this basically means that one is smaller, right? So if the first one is smaller, that's the one you want to copy into the original one. So you have this bigger array, bigger list, you want to compare these two. This one is smaller, so you copy this one here. So I'm going to take another k, which is 0, and I'm going to use this as the index in the A list that we have. A1I, k is equals to k plus 1, I is equals to I plus 1. Because you have used A1I, you need to move I. Okay, if that's not true, in that case, I'm going to copy A2j, k will still move and j will also move, right? Both of these will move. Okay, so what I've done here, so I'm saying compare these two, whichever is smaller, copy that. If you have copied this element, move I here, then you compare this and this, and k is also moving. Whichever is smaller, you put that element here and you move that one further. So this while will finish as soon as one of these two arrays, one of these two lists are done, right? As soon as you complete this one, even if j is still here, this while loop will stop, because you don't have any more elements in the first list that you have, so you can't compare anymore. So you need to stop, but you're still not done. You don't have all the elements in the output array, so you need to copy rest of these to the end. Okay, you need to copy the rest of the elements to the end. How do we do it? So you can just run while I less than length of A1. In case I is done, this loop will not run. In case I is not done, that means j is done. So you need to copy elements from the first one. Okay, so what's going to happen? One of these will get over. The second one will be somewhere in the middle, right? It still will not be done yet. So it's very, very simple. I will run a loop on I, and I'll also run a loop on j. One of these loops will not run because the index is already to the end. It's already at the end. The other one will run, and I'll just copy all the elements to the output A that we have. So while I less than length of A1, I can copy this code, right? So I'm copying A1I and I'm incrementing I and I'm incrementing k. I can write the same code for j length of A2, and I can copy the code from here. And I think we are done. I'm assuming that the list that is passed to me has enough space. I'm not using append. I'm assuming this list has enough space, which is true in case of merge sort. In case of merge sort, you did a split on the original list and you made two lists from the first part and the second part. So there is enough space in the original list that you can merge the two parts into the original one. So I'm assuming there is enough space in A. Okay, that's why I'm not using append. I'm directly putting data into it. Okay, let's see if this will work. Comma 2. Sorry, I should take an unsorted one. And let's call merge sort on it, and let's print A after that. Okay, seems like we made the perfect recursion error. We didn't write our base case in merge sort. So obviously we need to write our base case. If length of A is equal to 0 or length of A is equal to 1, I need to return. If the length is 0 or length is 1, I don't have to do anything, right? So I can just return. Let's run this again. Sorry. Let's run this again, and it's sorted now. Seems like it works. Okay, perfect. So most of the code was written here, but I think most of the interesting things were happening here, right? You decided that you want to split it into halves, and then you decided that you want to merge them together. Okay, and amazing algorithm, works really well. Let's quickly dry run this to see how exactly it is working. So this was our input, right? So it's a 7 length input that we have given. So we found the middle. So we gave length was 7 by 2 is 3, so 0 1 2 3, right? So this is 3. So we took this part on one side and this part on the other side. So that basically means we created this and we also created this. Now we're going to call on the first part. Once the first part is done, then we'll call on the second part, right? The calls are in order. So first the call is on this one. So when you call on this one, it comes to the merge sort, and this again is not of length 0 or 1, so we're going to divide it further. So it will get divided into 10 and 5, 3. First call will be on 10. But 10 will say, hey, I am length 1, so it will return right away. 5, 3 will say, I'm not length 0, length 1. So it's going to further divide itself into 5 and 3. Make a call on 5, it will say I'm done. Make a call on 3, it will say I'm done. Then you have these two sorted lists with you, and you are going to merge these two into the original one. 5 is sorted, yes. 3 is sorted, yes. You're going to merge these, and the merged list will look something like this. So instead of 5, 3, it will become 3, 5. Then you merge 10 and 3, 5 into the original list here. So this will become 3, 5, 10. Similarly here, now when this is done, it's going to make a call on 1794. So we'll split it into two parts, 1, 7, 9, 4. 1, 7 is going to split it into two parts, 1, 7. 1 will say I am sorted, 7 will say I am sorted. We'll merge these two into 1, 7, it will stay the same. 9, 4, you will split it into 9, you will split it into 4. And you will merge these two and it will become 4, 9. This is sorted, this is sorted. You merge these two, this becomes 1, 4, 7, 9. So you make these two calls in the induction hypothesis and you can actually see that they become sorted. And when you merge these two into the original one, the original list becomes sorted. So that's how things are running and that's how things are working. You're breaking down the list into as small as one element lists, and then those are by default sorted. Then you are merging those small ones into 2, then those 2 becomes 3 or 4, and that's how smaller lists combined gives you the original list, which now is sorted. Okay, so that's how things are working. I will definitely recommend you to dry run your code as well. Take a couple of examples, try to dry run and see how things are running. Okay, thank you. Hi. So in this session, I want to discuss another very interesting algorithm called quicksort. As the name suggests, quicksort is really quick. So again, a sorting algorithm. Again, much better than insertion, bubble, and selection. Arguably better than merge sort. So we can argue either ways. We'll talk about whether which one is better. Like we'll try to quantify all of that in the next couple of lectures when we'll be talking about time and space complexity. But for now, let's just take care of it. Let's try to learn the algorithm without worrying about whether it's faster than merge sort or not. So what is quicksort? So quicksort says, this is my list, right? Quicksort says that let's do one thing. Let's pick one element, one number, make it reach its right place. So 3, if you look here, after 1 and 2, 3 will be the next number in your list when it is sorted. So 3 has to come to this particular place. So it says take 3 to its required place. Pick any number, make 3 reach, take 3 to its right place. So you will make the list to be this. And now it says do something that everything smaller than 3 comes on this side and everything greater than 3 moves to this side. Okay, so we need to find an algorithm which basically what it does is, given a list, picks any element, finds its proper position, takes this element to its proper position, then it makes sure that everything on the left is smaller than this particular number and everything on the right is larger than this number. This does not mean the array has become sorted now. For example, I could end up with something like this. So 3 is at its right place, everything on left is smaller than 3, everything on the right is greater than 3, but the list is still not sorted. And we can decide if you have multiple 3s, what are you going to do? We'll take care of that as well. For now, let's just worry about that we have unique numbers. And once you're able to do this, then you can simply call quicksort on this side and quicksort on this side. These are smaller lists, so quicksort should be able to handle them. Base case, length 0, length 1. So length 0 and length 1 list is already sorted, you don't have to do anything. Then what do you do next? You partition your list into 2 halves such that there is a number in the middle. We can call it the pivot point. Everything in the left side is smaller than the pivot, everything on the right side is larger than the pivot. Okay, and we call it partitioning. So once you have partitioned it, you can call quicksort on one side and quicksort on the other side, and then the whole list will be sorted. So how is it different from merge sort? See, merge sort was just calling on the 2 halves. It was not doing any work upfront. Quicksort is doing a lot of work upfront, when the division is done, then it's calling recursion, like then it's making 2 recursive calls after the work is done. Merge sort was different. Merge sort was saying call merge sort on first half, call merge sort on second half. Now assume these two are sorted and then merge them together. But quicksort is doing a lot of work early on and then calling recursion afterwards. Secondly, I like quicksort a little better because you don't have to make copies. In case of merge sort, you have to make those 2 copies, the smaller, the first half and the second half. In quicksort, you will not need to create any extra space, any extra list. Everything will be able to manage that within the given list. Okay, so the code will look something like this. You'll get the array. You will have the base case. Once you've taken care of the base case, you will call something like a partition function. So it should partition your list into 2 halves, and it should give you the index around which it has partitioned. So there will be some index where your pivot element is, and everything on the left is smaller, everything on the right is larger. Once you reach this place, we just need to call quicksort again. On our own list, we don't want to make a copy, so we will pass starting index and end index into it, so that we don't have to make a copy. Otherwise, you'll have to make a copy of this part and this part. I don't want to make a copy, so for this part, I'm going to say from starting go till here. For this part, I'll say from here go till the end. So I'm going to get a start index and an end index. So the first half will go from start till I minus 1. Then I'll call quicksort on. It will go from let's say I plus 1 till the end. So my base case will basically be so 0 or 1, right? Length 1 is also sorted. So if S is greater than equal to E, this basically means either S has crossed E, it has crossed E. In that case, we can say that the array is empty, the list is empty. Even in case they are equal, there is only one element. So there is no sorting required as such. Okay. So this can be my base case. So I have my base case. I need to write code for this. And if I'm able to write code for this, I'll be done. Right. So let's quickly see how can we, given a list, we need to partition it into 2 halves. So let's say we are given this starting index, we are given this end index, and we just need to work within this part. We don't have to look outside this. Right. So we need to partition within this. So what I would suggest is, let's pick the first element itself. Right. First of all, let's make this element reach its right position. To do that, let's go through this list from S to E, starting index to end index. Let's say this pivot element is P. Let's count number of elements less than P. So if you find that there are 5 elements which are less than P, that basically means you need to move P by 5 position. You need to make space for those 5 positions because they will come before P. Right. So you count number of elements. Let's say this is C. So you move your element from Si to Si plus C to make space for those elements. Now, this is Si, this is an index. You have moved your pivot to this place. Right? Pivot is at its right place. What do I do now? Extremely simple solution. You take an I at the beginning, you take a J at the end. If this number is less than P, then this number is at the right place. It's fine. We can move on. If this number is not at the right place, then wait. Check for the last element. If this number is greater than P, then this is fine. Move it. If this number is less than equal to P, or let's say less than P, then we can swap this number and this number. So basically, what are we saying? This is my pivot. I start from the beginning, I start from the end. I keep moving this, I keep moving this. I'll stop as soon as I find an element here, which is larger than P, and I find an element here, which is smaller than P, and I'll swap them. And then I'll keep moving. So basically, you start from here, you keep moving till you can find elements which are less than P. As soon as you find something which is greater than P, you stop. Then you start looking from this side. As soon as you find something which is less than P, you stop. And as soon as you stop, swap both of them. So both of these have reached the right place. So this way, you will keep moving, and in the end, you will reach the middle point. And once you reach there, both the sides will have the required elements. That basically, what was the requirement? Everything here, everything on left has to be less than P. Everything on the right, I'm saying it has to be greater than equal to P. Not less than P, but greater than equal to P. So if you want to take care of equal cases as well. Okay. And if you are able to implement this, implementing quicksort is extremely easy. Okay. So that's what you need to implement. I had already written the pseudocode as well. So in quicksort, you will have the base case. After base case, you will call this partition. After partitioning, you will call quicksort on 2 halves, which is basically starting index till this point, and from this point till the end index. Okay. So please try to code it yourself. Watch this particular video as many times as you want. If you want to again go through this to understand how much to move P by, where exactly it should move, I have explained all of that here. So please try to code it by yourself because that'll give you a lot of confidence. Okay. Thank you. Hi. So in this session, I want to write code for quicksort. Okay. So let's get started. So I will have a function which will be quicksort. Quicksort will take a list, and as we discussed in the last session, we will need start index as well as end index, because we don't want to make copies. In recursion, when we will be calling again, we want to pass these start index and end index. Wherever you will be calling it from, by default, you can call it with, let's say, my list is this. Right? So I can call it with a comma 0 comma length of a minus 1. So that is my start index and end index. Okay. So first of all, the base case. In case your starting index is greater than equal to end index, that basically means either starting index is crossed end index or they are equal. If they have crossed, the length is 0. If they are equal, the length is 1. Both the cases means your list is sorted. You don't have to do anything. So we can return. Right? We can just return. Now I'm going to write a partition function. So this partition function is going to need the list and what area of the list to partition, right? What area of the list to partition. And I would get this function to tell me the pivot index, right? I will make this. So if this was starting index, this was end index, it will partition my list, this part of my list on basis of this element, and it will tell me after doing the partition, after moving things around, where has this element gone to. So I would need the pivot index. Once I have the pivot index, I can call quicksort. See, the good part about quicksort is after you've done the partition, there will not be any movement between these two sides. So you can just, if you sort this part and this part, this area is sorted. Because everything smaller is here, everything larger is here. So if you just sort this and sort this area will become sorted. So we'll call quicksort starting index till pivot index minus 1. That's the first half. These parts need not be equal, right? It's possible that we have only 2 elements here and 5 elements here. That's fine. So quicksort, and this time pivot index plus 1, and we'll go till end index, and that's it. That should sort our list. Okay. Now let's quickly write the partition function as well. So you will pass this. So how do we partition? Okay, let me just remove this. Okay, so how do we partition? So I said, so first of all, if it's of length 0 or 1, again it doesn't make sense to do anything. So just for the sake of completeness, if it's greater, I'm going to return minus 1 because it's not relevant. It's not going to happen this way, right? Start index and end index will be proper because when you're calling partition, you've already checked before that they are proper, right? So let me just get rid of this. I'm not writing this. So my pivot is a of si, the starting element. So if this is the area, starting index and index, I said this will be my pivot element. So that's the pivot element. The second step was find number of elements smaller than pivot, because if you find that, then you would know how much to move pivot by, right? What is the right position of pivot? Okay, perfect. For I in range, I want to go from start index, I want to go till end index, so I'm going to say end index plus 1. Okay, so I want to go from starting index to end index, so that's why I'm saying starting index to end index plus 1. Okay, if a of I is less than, and I'm planning to keep everything less than p on the left side, greater than equal to p on the right side. Okay, so equal elements go to the right side. So if ai is less than pivot, then I need to maintain a count. So let's take a c, which is 0. C is equals to c plus 1. So when you complete this for loop, you should have the number of elements which are less than the pivot. So we need to move pivot to a position accordingly. So where should we move it? Currently it is at si. We need to make space for c elements to it, so it needs to go to si plus c. Okay, that means a of si plus c should become a of si. I hope you understand that I can put 2 things on the left and 2 things on the right and it will work fine. And so I need to swap these two, and I'm swapping them in a single line, right? So si plus c and si. Don't try and replace si with the one at c. That's going to be a problem. Let's say my start index is 30, end index is 50. I find 5 elements which are smaller than my pivot. Then you don't want to swap this number with index 5. You want to swap it with 35. So that's why si and c should not be swapped, Si and Si plus C should be swapped. So your pivot is swapped here. Okay, so I've swapped the pivot. So my pivot index, let me just store that, is now Si plus C. Right, that's my pivot number. Now what do we need to do? So we have Si, we have Ei, pivot has reached its place. Now we need to take an I which starts from here. We need to take a J which starts from here. We need to move them till they reach at one place. And if this is smaller than the pivot, perfect. Right? Move to like increment I and then check again. If J, the element at J is greater than equal to the pivot element, perfect, nothing to do. In case both these conditions are not met, that means you have an element here which is greater than pivot. You have an element here which is less than pivot, swap. Right? You swap. And then you keep moving forward. Okay, let's write code for this. I not 0, Si. J is equals to Ei. I need to do some work while I less than J. I should be less than J. If I and J are equal, they are at the same element, that will be the pivot element. So they will move and meet at the pivot element. Okay. So I don't have to do anything in that case. So while I is less than J, what do I need to do? If A of I is less than pivot, this is perfect. I is equals to I plus 1. In case that's not true, then let me just remove these brackets. I don't like them. So in case that's not true, then I need to check. Okay, so that's not true means I have found an element which needs to be moved. Then I'm going to find an element on this side as well which needs to be moved. So else if Aj greater than equal to pivot, that means this is not the right element. I'm going to do J is equals to J plus 1. Sorry, J is equals to J minus 1. In case both the conditions are not met, that means Ai is at a wrong place and Aj is also at a wrong place. Perfect, you can swap. So this else is where you need to swap the elements. Okay, Ai comma Aj is equals to Aj comma Ai, and we have swapped the elements. Both the elements are swapped. Now you can do I is equals to I plus 1, J is equals to J minus 1. I think this should do it for us. Okay, and eventually when you're done with your function, you can return pivot index. You can return the pivot index. Okay, so now before running quicksort, let's quickly run partition on an array and see if things are working correctly or not. So let me just put a 6 here and let's call partition on this. So I'm going to print whatever partition returns and I'm going to see what A contains. Okay, so seems like 6 has gone to the right place. Everything on the left of 6 is smaller than 6. Everything on the right of 6 is larger than 6. The left side is still not sorted. The right side is sorted by coincidence. It was not compulsory. We didn't done anything to sort it. By chance it is sorted. Okay. Seems like the partition, at least in this example, is working fine. Okay. So now let's take a chance and see if quicksort itself is working fine or not. Length of A minus 1. I will have to run this cell. Let's run this, and we need to print A as well, and seems like this is sorted, got sorted. Perfect, that's what we want to do with quicksort. We can dry run it once quickly, so let's try to dry run it quickly. 87135542. So the first time we will partition on basis of this. We'll see how many elements are smaller. 1 2 3 4 5 are smaller. So the first thing it will do, we'll keep 5 spaces for those smaller elements and swap with the next one. So 6 will come here, 1 will come here. Then we put an I here, we put a J here. This element is perfect. So Ai is less than pivot, so we'll move I. Now Ai is not less than pivot. Aj is not greater than equal to pivot, so it's going to swap. So 2 comes here, 10 goes here, and we move both of these. And now you compare 9 and 4. Sorry, you compare 9 with 6, problem. 4 with 6, problem. So you swap 4 and 9. Why did I say problem? Because 9 is greater than 6 and 4 is less than 6. Both of them are at the wrong place. So you put 4 here and you put 9 here. Then in this particular example, we are seeing a lot of swaps. It's not necessary. So 8 and 5 will get swapped and 7 and 3 will get swapped. And that's exactly what we saw when we called the partition function. That's what you're getting. Now you will call quicksort on this part and quicksort on this part using exactly the same logic. It will keep splitting your list into smaller parts and eventually sort the whole thing. Okay, perfect. So if you are not able to code quicksort before looking at this session, please make sure that you write it now. Do not copy paste code. Please write it from scratch and watch the hint again and again as many times as you want, but make sure that you code it, because this will give you a lot of confidence. Like, this is actually being able to write quicksort and merge sort is kind of an indicator that you are understanding recursion in much better ways. Okay, thank you. So in this session, we want to pick up a problem which is one of the most, I would say, one problem that everybody does when you're doing recursion, but is extremely simple, but extremely difficult to understand as well. Right? Like the solution is very, very simple, but it's so simple that it makes it almost unbelievable, like impossible to believe. Right? So the problem is tower of Hanoi. Okay. So what is the problem that we want to solve? So we are given three poles. The first pole has some disks in it, right? Let's call it A. You have to move all these disks to C. You can use B as a helper. Okay, so this is your helper, this is your source, this is your destination. You need to move all of these to destination, and you can use B as a helper. There are a couple of rules. First of all, you can pick only one at a time. So I can only pick one disk at a time and move it. So first rule is only one disk at a time. Second rule is, the way you see here, the way I have drawn it, the largest disk is at the bottom, then the larger, then the smaller one, then the smaller, and the smallest one is at the top. At any point, a larger disk cannot be put on a smaller one. Right? So this is fine. If I had these two here, that is fine as well. But you cannot have a larger disk sitting on a smaller disk. Okay, these are two rules that you need to follow. And we need to print all the steps that we will take to move these disks from A to C. Okay, so we need to move all these disks from A to C, and you need to print all the steps that you will need to take. Okay, so now if you think of it, like you can say, okay, I'll move this one here, the first one to the helper, the second one goes here, then I can't move the third one anywhere. So like if you try to think of it like by yourself, it will be really complicated. Okay, but let's think in terms of PMI. What does PMI say? If I have only one disk, things are super easy. I can just move that disk from A to C. So if I had only one disk, I'm sorted. If I have n-1 disks, I can assume that I can move them from one pole to another using a helper. So the situation has to be exactly the same, in the sense that I can move n-1, but I need to have an helper as well. And I need to make sure that the destination is also there, right? So the condition has to be exactly the same. But using induction hypothesis, I can say that up to n-1 disks, I can take care of. I don't have to worry about them. Now my work is to manage these n disks. Up to n-1 is fine. So one solution that some people give is basically this. If you can do n-1, why don't you move these n-1 here, right? Why don't you move n-1 here? So one solution a lot of people give is, hey, why don't you move the smallest disk here, right? Or let's say the smallest disk here. Now you know how to move n-1, so move these n-1 to the destination, and then you can put this one on top, right? So what am I saying? So first move the smallest one to the helper, then rest n-1, you can take it here using induction hypothesis, and then move the small one to the top. Now there's a problem with this solution. Here you have this. So this is not the same problem as the original problem. The original problem had the helper as empty. Helper was empty. Now the helper has a very small disk over which I cannot keep any other disk. So helper is effectively useless for me. In the original case, in the original problem that I was given, the helper was absolutely empty. So I could put anything on helper. But now if you see, helper is actually blocked for me. So I can't move this n-1 here using induction hypothesis, because induction hypothesis says that I can solve the exact same problem for up to n-1. What is the exact same problem? The exact same problem is that I can move n-1 to a destination using a helper as long as the helper is empty, or I can consider it to be empty. Right? So this solution is not going to work. You can't just move one to helper and then n-1 to destination and then one from helper to the destination. That's not going to work. So what's going to work? We can do something like this. Let's move these n-1 to the helper using the destination. Helper is empty, destination is empty. I can move n-1, that's not an issue. So I can move n-1, but instead of moving to destination, I'm moving to helper using the destination. So the next state will be, there'll be one disk here, there'll be these many disks here. So you'll be in this state. Now move this disk here. So the largest disk we have moved to the destination. Now the good part about the largest disk is it's as good as the ground, because it doesn't restrict us from anything. You can just put anything on top of this. This is as good as ground. So first you move n-1 to helper, then you move the largest disk to the destination. Now you can move these n-1 to the destination from the helper using the source as helper, right? So I can move from B to C and I can use A as the helper, and I've reached the desired goal, which was this, right? So the largest disk is here and I will to move n-1 here as well. So my code will be extremely simple, right? Base case, if n is equal to 1, I'll just simply print move the nth disk from A to C, right? As simple as that. Now the next step, move, this is base case, I'll move n-1 from A to C to B using C as the helper. Nth will go from A to C. Now n-1 will go from B to C using A. That's what we need to do. This is a recursion call and this is a recursive call. This is a single step for which you don't need recursion. You just print it out. Okay, so your function will look extremely simple. It will have basically a base case in which you will be printing something. It will have this recursive call, then you will have some print statement here, then you will have another recursive call, and that's it, will be done. Okay, so quickly write code for this. It's going to be very simple. Just tie and replicate exactly what I said, that you need to worry about moving n-1 from A to B using C. Now move the largest disk from A to C, and now move these n-1 from B to C using A as the helper. Okay, perfect. Please try and code this. You will really enjoy, like if you're able to do this, then you will really enjoy that feeling, because it's going to be very small code and it's going to give you a feeling that you were able to achieve something that it will be very hard for you to do it by yourself, right? Perfect. Good luck. Thank you. Hi. So in this session, let's write code for Tower of Hanoi, right? So once we write the code, we'll dry run it. We'll try to see how exactly it is working for n is equal to 2, n is equal to 3, n is equal to 4, and so on, right? So hopefully things will get very, very clear once we try and dry run as well. Okay, let's write code. Tower. So I'm going to get input n and a, let's me call it A, B, and C, right? So A, B, and C are the name of the towers. So these are strings, and n is an integer. So I can take n is equal to 0 as a base case as well, or n is equal to 1 as the base case. I'm just taking n is equal to 1 as the base case. So I'm going to say print move first disk from A, to C, right? So we'll just move that disk from A to C. Okay, perfect. Now we discussed if we are not at the base case and we need to return, right? We are done. So if it's the base case, you just move that and you return. You don't come down. Okay, so I'm going to return from there. So called Tower of Hanoi on n-1. You move these from A to B using C. So B and C are role is reversed. So n-1 have moved from A to B. So the current situation is this, this, and this. Okay. Now we're going to move this single disk to C from A. Okay. So similar print. Let me write it again. Print move. This is the nth disk, the largest disk. So move nth disk from A to C. So the nth disk has been moved from A to C. And now the current situation now is this is empty, this has n-1 disks, and this has one large disk here. Okay, so now we need to move these n-1, and they need to go from B using A to C, right? That's what we need to do. Okay, so we need to move n-1 from B to C using A. Perfect. So let's run this. Let's start small, right? Let's start from 1. Source, helper, destination. So it's saying move the first disk from source to destination, which is correct, right? That's what you need to do. Let's try for 2. So for 2, it's saying this is the situation. It's saying move first from S to H. Okay, this comes here, the smaller one. Second from S to D. Second goes here. Then first from H to D. Perfect. We are able to move 2. Right? 2 works. Now, what I want you to do is assume that 2 work. We already know that 2 disks are, we are able to move 2 disks. So just assume that 2 disks are going to work fine. If you're going to assume that, let's see how 3 are going to work. Because you know how to move 2 disks, you can move these 2 here, and then you can move this large one here, and the large one doesn't disturb anything. It's like ground because it's at the bottom and it's the largest. Putting anything on above this is not going to be a problem. So you can move these 2 here as well because you already know how to move 2 disks, and we're able to move 3. Using exactly the same thing, you'll be able to move 4, and so on. That's the beauty of recursion, right? While we were writing code, we didn't have to worry about how n minus 1 is going to work. We just assumed, and once we have written the code, it actually works beautifully, right? For 4, it's giving you the complete directions, what you need to do. Please try and write this code from scratch, and it'll give you a lot of clarity on what's happening. And then do try to dry run for up to, I would say, 4, because that'll give you a sense of how exactly recursion is solving this particular problem. Okay, perfect. That's about it. Please work on the assignments because those are the things, those are the questions, those are the problems, and that's the work that's going to give you the maximum confidence as well as the maximum knowledge. Right? Just watching me code is not going to work. What's going to work is you writing a lot of code. The more code you write, more confidence you'll feel, more problems you'll be able to solve, and like it's all about getting that feeling that I can write code for whatever problem comes my way. Right? So solve a lot of problems. It's basically just math. The more problems we're going to solve, better we'll feel about our concepts and our ability to solve new problems. Okay? Perfect. Thank you.